I have the honor of chairing this session. The first talk will be given by Dhireesha Kudithipudi from Rochester Institute of Technology, and her talk will be about performance efficiency trade-off of low precision numerical formats in deep neural networks. Your talk, please.
Hey, good morning, everybody. I'm really honored to be here. I've been working with John on Posit-based deep neural networks for over the last year. This project that I'm going to talk about has started almost a year and a half back, as Hamid here, one of my PhD student, was doing his PhD qualifying exam. That's where he stumbled on posits, and he got really excited about how they can be applied for deep neural networks. So my research lab focuses primarily on designing neuromorphic computing systems, brain-inspired algorithms, and hardware, and also looking at how to do energy-efficient deployment of machine intelligence. And that's where this research fits in place. So in today's talk, I'm going to focus on how can we design low-precision deep neural networks, or I would like to call these ultra-low precision deep neural networks, and what are some of the trade-offs. So the earlier part of this work is published in Date, or it will be presented in Date if any of you are more interested in the lower hardware level details. Unfortunately, the primary author, Zach, couldn't come here because he chose to go to Italy instead of Singapore. So, before I delve into why we are using or exploring these different ultra-low precision formats for deep neural networks, let me give you a little bit quick snapshot of why we are interested in this approach. So I think the previous talk really summarized some of the key points on why we would want this low precision for deep neural networks. So if you look at a deep neural network, these are highly connectionist, dense networks, and they're doing prediction models for tasks like classification or regression. So in general, DNNs learn some nonlinear input to output function by minimizing an objective. And this could be done in a supervised fashion, in an unsupervised fashion, or a semi-supervised fashion. And the most general approach is to kind of minimizing these gradients using backpropagation with labeled data. And of course, I don't have to emphasize that this has been very successful in multiple domains, including vision, NLP, genomics, and several others. So one caveat with these networks is that they're really hungry. They're hungry for power. They're hungry for compute resources. So here is an example network, an LSTM with mixture of experts model. It requires about 137 billion parameters and about 548 gigabytes memory with a 32-bit float implementation. So that's pretty heavy in terms of memory or compute resources. So if you look, if I go back, at the heart of all these networks, you see these circles. Which of those is a neuron? And the heart of this neuron is a very unassuming multiply and accumulate operation. So it seems like this multiply and accumulate operation should be cheap, but if you think of really large-scale networks, you require a multiply and accumulate unit for each of these neurons, and it can pretty soon become a very compute resource-hungry implementation. And depending on the type of task you're trying to do, there is loads and loads of data that you have to move through this network. And I think, again, as the previous talk mentioned, data movement cost is really, really expensive. So in a lot of our networks, we did analysis that the data movement cost in these networks could be anywhere from 70 to 80% of the total power, so power budget for the network. So that's really expensive. And the DNN parameters, so in this case, we have about 137 billion parameters, and those also require memory, and that's not cheap either. So if you look at the two faces of this, of a DNN network, at a high level, we are training a given network with loads and loads and loads of data, and we are doing evaluation of the efficacy of the given network for a given task. And if you are not if the network does not give us good results, you're going to fine-tune all these hyperparameters iteratively. And then this is all in the development phase, and in the deployment phase, you're primarily doing inference. So a lot of my research lab focus actually does learning also in the deployment phase, where you continually learn even after you deploy. But in this project, we are focused right now at this point on inference during the deployment phase. So how can these deep neural networks be deployed not on high-end compute platforms, but on really low-end embedded platforms without sacrificing performance? Usually, one of the caveats the hardware designers we think about is like, when I'm deploying something on a low-end embedded platform, it is okay to compromise on accuracy. But there are certain class of applications where we cannot compromise on the performance, and how do we actually achieve this? So there are several techniques, and there is a large body of research that's been happening in this area over the last few years. People have been using different kinds of techniques. You could do, instead of these dense networks, you could kind of do sparsity in your networks. You could do some kind of pruning of these networks. You could do neurogenesis. You could do all kinds of tricks, different plasticity models to kind of optimize these networks. And one natural fit is, a lot of folks have also been looking at low precision implementation or low precision arithmetic in implementing these on low-end embedded platforms. So when we're talking about low precision arithmetic, a lot of earlier research has shown like how much energy savings or power savings you could have when you move from a 32-bit floating point to an 8-bit floating point. It has been shown that you could have 4x reduction in the data movement cost, and also 4x reduction in the compute resource utilization. And that is significant savings when you're moving from 32-bit to 8-bit. So, and in a lot of this work, what they try to do is, when you're using this low precision, you have to quantize. And there are different kinds of quantizations that you could use. And a linear quantization, where you're doing some kind of shifting or multiplication, or nonlinear quantization, where you're using some kind of k-means clustering mechanisms to do the quantization. These are good, but what happens is, when you're doing these kind of quantization mechanisms, there is a price you pay. There's no free lunch, right? So you are paying some price in terms of adding additional compute resources on the device, on your end platform. And especially if you're doing your quantization at the inference phase, then you might have to retrain your network, and it might require an increased number of hyperparameters in your deep neural networks. And there is a other very naive quantization approach, the direct quantization, where you can round to the nearest even, and there's no compute overhead. Again, if you're doing it in the inference phase, some of this retraining might have to happen. So in this approach, or in this project, what we do is we do the quantization, but we also do this clipping, basically to address the overflow and underflow issues. So as I said, there is a wealth of research in this domain in low precision implementation, particularly from the industry side, because they're heavily interested in the inference stage, whereas the academic research community is more interested in the training or on-device learning phase. So, but a lot of these comparisons have been looking at a 32-bit float versus an 8-bit float, or the tasks have been different, or the underlying hardware units have been different. So we felt that there needs to be a really fair comparison between these different low precision numerical formats. And of course, in this, a lot of earlier work, posits haven't been looked at how they fare with these kinds of designs. So we look at these three formats and see how they work with this DNN inference. I don't think I have to talk about posits. We've talked about enough about that since yesterday, and I've given some great introductions about posits. And one interesting factor about posits is the tapered precision. That's what is intuitively interesting for us for this deep neural network inference. So on the left here, you look at the plot of the weight distributions of a convolutional network for a single layer. And you could see that there is this heavy clustering around 0. And on the right here is the posit value distribution. This is an 8-bit posit with ES equal to 0, and you can see a similar heavy clustering or that tapered precision. So this is for a single layer, but we have done this histograms over last summer, I think, with several late night meetings with John. If you remember, I think you encouraged us to look at different kinds of deep neural networks so that you see this behavior is consistent across all the networks, and we averaged it across the layers, and we see that this kind of behavior is consistent for all these networks. And if you look at the quantization error, you could see that it is also lower near the center because of that tapered precision. So that is really what caught our attention. So that seems like there is some match in here where you could use these posits for DNN inference, especially if we are trying to do this in low precision bits. So earlier work has looked at hardware implementations with a low precision, but a lot of those MAC units have been, or the multiply accumulate units, are not exact multiply and accumulate units. So they're either doing preemptive rounding or truncating or different kinds of inexact operations. So the idea here was we use an exact MAC as a baseline unit for all the different numerical formats, all the 3 numerical formats. And I think there has been enough discussion about this, this kind of EMAC unit where you want to use a wide accumulator architecture so that it remains still resource efficient at low precision, and we kind of delay the rounding and truncating until all the sum of products is computed. This sounds very familiar to you. It's the coolish exact dot product. And the reason I have that in the next slide, but the reason we didn't use EDP in our paper is because it's often confused with the energy delay product EDP, which is used in the hardware community. So that's why we use the EMAC term. The size of this wide accumulator can be just calculated using the carry bits and looking at the dynamic range, looking at the min and max absolute values of the specific format. So you can calculate the size. And as I said, this is nothing but the coolish exact dot product. Okay, so for the next 3 slides, I'm going to show the hardware design of the 3 EMAC units. So we wanted to, as I said, keep this comparison fair. So for all these EMAC units, we have 3 inputs, the bias, the weights, and the activations. All of these are parameterized. N bits in here is the number, and we have the Q fractional bits. And rounding here, we are doing it after the accumulation, and we are rounding to the nearest even. As I mentioned, it's a direct rounding process. And we are resetting this wide accumulator using this bias term at the beginning of each dot product, so you could have a diverse set of biases in there. And no underflow or overflow values because we are doing the clipping to max. So you can think of this as a baseline for the fixed point. And I don't know how well you can read this. This is this is for the floating point EMAC, and you can see that it still has the same 3 inputs, the bias, weights, and activations. And again, parameterized, and we have WE exponential bits and WF as the fractional bits. So in our design, we did not use the not a number or plus or minus infinity, primarily because we don't see this in DNN inference, but for later implementations, if you're doing it even in training, we have to consider some of these things. So as with the floating point, you need to do the subnormal detection. So we try to do the subnormal detection here before it's doing the multiplication, and we do the exponent and mantissa packing. And the biased exponent here again, so here we have this bias in here. So it is used to shift the product into fixed point representation for the accumulation. And we use a single leading 0 detector to encode the exponent and extract the mantissa, and here we are normalizing to get our output. So we use a single unit to do both leading 0 and leading 1 detector by just using the 2's complement to reduce some overhead there. And the Posit parameterized EMAC, again, it has the same 3 inputs, the bias, weight, and activation. And we are decoding them, and I'll talk about how we are decoding. And then doing the sealing with the log base 2 of the input. And again, in this case, we are not considering the not a real because similar to float, we do not see this in the DNN inference stage. And the biased exponent, again, in this case, is used to shift the product to its fixed point representation for accumulation. And we are doing normalization here, again, to extract the output. Again, the single leading 0 detector is used to encode exponent and extract the fraction bits. So the regime is dynamic. So we have a very simple algorithm on how we are going to extract the posit for n input with ES exponents bit, and we have the whole algorithm in the paper for how we did the posit EMAC. I didn't want to put that whole in here, so you could just go through it. So for the decoding, the regime and exponent can be extracted naturally. If you're shifting posit by a certain regime bits, we get E and the F, the exponent and the mantissa, and we use a single leading 0 detector to extract the regime bit. And ES bits here and here is going to give E, the exponent. So the scale factor can be achieved by simply concatenating this K and E. So this is our scale factor. And in this example, I don't show if sign is 1, but you just have to do a 2's complement and perform the same operation. So if R is 1, we are trying to do the negation, so we don't have to use the leading 1 detector. We are just doing the 2's complement in there. And in the encoding process, we are doing similarly. We can get K and E from the scale factor, which I've shown earlier. And the absolute value of the K shifts, which is the regime shifts, E and F into the place. So if you have a positive K, like in here, you just do the arithmetic shift, and everything to the right of this here is the sticky bits. And if it is negative K, then you're just doing the shift by absolute K minus 1. And this is just an example to show that how you would verify this. So that's what we do with the posit decoding and encoding in that hardware implementation. Okay, so now we have the building blocks, the exact max, and we are just going to drop them in into a deep neural network. And did you see this name here, deep positron? This is John's idea again. He calls this positron. I don't know if you remember this. So if you're more in the machine learning community, you know the perceptron is a common term. We call multi-layer perceptron. So posits with perceptron implemented using posits is the positron. So this is John's suggestion. Yeah, Yamamoto. Okay, okay. So at least we heard it from John first. So what we did was we plugged in all those EMACs for all 3 realizations, the fixed, floats, and the posit. And we have local memory per EMAC depending on the DNN parameters and the type of tasks we are doing. And for the hidden layers, we are using the ReLU activation functions, the rectified linear unit. It's the simplest one for hardware implementation. And then the output is just a linear readout layer. And again, as I said, we did this part of the project only on inference, but we are extending it to training currently. And we've deployed or synthesized this on a Vertex 7 FPGA. Okay. So we looked at 5 different tasks in our implementation. The first 3 are really baby tasks. And but because we are doing a hardware implementation, we wanted to see initially how it performs with these simpler tasks. And then the last 2, I think you're probably a lot of you are familiar with MNIST. It's a handwritten digit classification. And then the last one is Fashion MNIST, which is kind of a drop-in replacement of MNIST, but for clothing classification. So you can see this, you identify different clothing. So we look at all these 5 tasks. The software implementations, we've looked at ImageNet and other bigger data sets, but in the hardware, we kind of stick to smaller data sets. So in the experiments, what we did was we did a high precision training and did the low precision inference, and DNNs trained with 32-bit floats. And we did the direct quantization, and we tested for bit widths from 5 to 8. So we call this ultra low precision because we're looking at bit widths less than 8 bits. And we format the parameters or swept some of these parameters during inference. So we looked at the quantization error. It's just the mean squared error for all the tasks. So here I show primarily MNIST on the left here, the quantization error, and the fashion MNIST on the right. So here we are looking at posit compared to fixed on the top and posit compared to float. So in all cases, we see that, so here is the bit precision. I don't know, it's very hard to read on this. So 5 bits to 8 bits. So the 5-bit posit always shows like the lower MSE, even averaged across the layers, or averaged overall average also shows that 5-bit does much better. So if we look at the actual task results, this is for the 8-bit, and this is across the different data sets and the size of the inference. So this is like, I mean, if you look at the machine learning community, as I said, these are like baby tasks. But if you look at the accuracies, this is the 32-bit float, and this is the posit, float, and fixed in 8-bit. So you can see the accuracies of posit in here are comparable to 32-bit floats. This is really very interesting. So if you look at, for example, MNIST, with 32-bit float, we got 98.5%. Again, we didn't use the state-of-the-art CNN to get that 99.99% accuracy, but we use that MLP implementation. So you have this 98.5%, and with the 5-bit posit, we get the same accuracy for ESS1. Similarly, like for IRIS data sets, you can see that the accuracy is the same as the 32-bit float. But in general, you can see that posit performs better than the float and fixed point in terms of accuracy across all the tasks. Okay. So that's very useful when you're trying to do low precision inference on edge devices. Okay. So that was for the 8-bit. But when we are looking at lower than 8 bits, like 5 to 8-bit widths, we wanted to see how it does across different metrics in terms of power, delay, and the energy delay product. So here on the x-axis, we have the average accuracy degradation and the dynamic power. And you really need magnifying glasses to look at this. But we have 3 different color codes here. Yellow is fixed, and blue is float, and green is posit. And the stars here, so you see, what happened to this? Oh, I think the battery is dead on this one. Okay. So the stars are representing lowest accuracy degradations. So the greens are the posits. So you can see that posits have the higher dynamic power, especially when you're using higher ES values. So when ES is 2, you'd see compared to ES is 0, that you would see that the power kind of grows exponentially in there. So whereas you could see that floating point can be realized with a lower dynamic power requirement than posits. Posits with ES is equal to 0 seems to have like comparable power consumption with floats. And we did the same thing with delay. And we see, obviously, as expected, fixed point exhibits the lowest latency but worse performance. And posits kind of outperform floating point in both bit width and also in latency across 5 to 8 bits. So for all bit widths, we see that posits outperform floating point in terms of this latency. But again, the caveat is that as ES increases, posits latency also increases. And when we are looking at the energy delay product here, again on the x-axis is the accuracy degradation, on the y-axis is the energy delay product. Fixed points, as expected, exhibit the lowest EDP, but they show the worst performance, as we have seen earlier. Posits have better performance or accuracy compared to floats or fixed at this ultra-low precision. And posits...
How many exponent bits are in your 8-bit float?
So we have different ranges here, so you could see, I don't know, you can't even see here. We have 3, 4, so we have different variations of it, yeah. I'm sorry, I converted it to PDF to avoid issues with PowerPoint, but it looks like that didn't help. So floats generally have a lower energy delay product, but again, we did not do like a full IEEE 754 implementation considering all the clauses. So I think the next steps would be to actually to see if that would still show the same results in terms of energy delay product compared to posits. So if you want to look at energy efficient applications or implementations, then ES equal to 1 is a better fit, and ES is 2 is a better fit for more accuracy dependent applications. There are few implementations of posits available. I think if you look at different Vertex 6 FPGA or Zinc implementation on different kinds of FPGA implementation, some of them have just done multiply, add, or subtract, and some have done like an FIR filter task. So our implementation of all this is on a Vertex 7 FPGA, and we use the Choir, and our implementation is in VHDL. Okay, so in summary, posits seem to be a natural fit for low precision DNN inference. And we have done different kinds of quantization, and we see this behavior consistent across other quantizations, and also we are starting to do the training, and we are getting some very interesting results. So depending on what you want on the edge, whether it's an accuracy critical task or whether it's a latency critical task or energy critical task, I think posits can be fine-tuned to achieve the task. I think we need to do a lot more optimizations on the EMAC implementation to do further extensive analysis on this. Thank you.
Okay, thank you for the talk. Are there any questions? Yeah.
Yes.
Just to make sure you never need, you never have an overflow in your EMAC in these applications?
Yeah, we are clipping.
But you never have such a large sum that you would risk to overflow? You're clipping at the ReLU, I'm not sure I understand.
Oh, we are...
The answer is probably that yes, there's no overflow because the wide accumulator is wide, but just to make it sure, because for small precisions, I'm not sure. The accumulator remains quite small.
The accumulator is, the wide accumulator that we used is 32-bit.
Yeah, so you never accumulate that many values.
Yeah,
okay.
yeah.
Okay.
Thank you for the presentation. I really appreciate the precision that you get at the end, having such a small format. But what is the latency comparison between having those 8 bits operation on this big accumulator compared to, I don't know, 32 bits floating point, standard floating point, or 8-bit standard floating point formats?
So obviously the latency takes an impact, right? I mean, when you're going to the smaller one, but we wanted to keep the comparison fair across the bit widths. Like all of them are like 5 to 8 bit widths, whether it's for posit, float, or fixed. So if you look at a lot of comparisons, I mean, I know the question is how does it perform compared to 32-bit float when you drop to the 8-bit or when you drop to the 5-bit. But in the last 3 plots that I've shown the results, we tried to be fair in the comparison, trying to stay with the 5 to 8 bits. But there is definitely a compromise when you're moving from 32-bit float to 5-bit in terms of performance in certain cases. But the idea is that we want to use this ultra-low precision for really low-end embedded platform. So the goal is, or the target is very different in a sense. It's very different compared to what designing accelerators like TPU, which are targeted towards high-end data centers where latency is of high importance, like, minimizing the latencies of high importance. Whereas here, the edge applications have very different constraints. So energy being one of them, and reducing the compute resources being the other, or the data movement cost and so forth. So it's a slightly different way of looking at the accelerator designs for these kinds of target zones.
So what you're saying is that even if you have conversion functions, POSIT to internal format operation on the Coolidge accumulator and the Quire accumulator, and then internal format to POSIT, you consume less than a 32-bit floating point unit, having the same output precision or result precision?
So, I think I'll hold off on that statement a little more, because the design is not comprehensive. As I was telling, the EMAC design is still missing some pieces, so I would hold off on making that statement still. Because, I could say today that it is lower, but I think it is, some of the functionality is not embedded in the EMAC, so I do not want to make that statement, yeah.
Okay, thank you. I think we have no more time for more questions. So let's thank the speaker again, Dhireesha.